So next, I'm going to talk about approximating areas under curves using rectangles, and I'm going to use the GeoGebra applet that we created for Lab 1. There's a separate video for the construction of this applet. I changed the function to be the function x squared. This is the function that we were looking at before, and you can do that by just double-clicking here, and you can make it whatever function you want. Additionally, I have set the zoom to be at an appropriate level, and I moved my points A and B to be at 1 and 3, my starting point and my ending point for the area under the curve. So as it's set up now, I have my number of rectangles. I'll click to move here. The number of rectangles is 4. I've set D at 0, and so that's going to set the height of the rectangle to be given by the left endpoint approximation. And another thing that I did is that you can go and view the spreadsheet view in addition to the algebra view and the graphics view. We aren't actually really going to need this view. I'm going to make it smaller because it's not important. And I'm going to keep track of what we've done. So here, when the number of rectangles is 4, the left endpoint approximation, as we found before, was given by 6.75. The right endpoint approximation you can find by going here and moving my d value to 1, and notice that my rectangles, it looks like they're growing, and they're growing because the height of the rectangle is given by the right endpoint. So the right endpoint approximation gives us my a value of 10.75, which is also what we found before. But the cool thing about GeoGebra is that it can do a bunch of computations for us without having to do them by hand. So let's say we want to up our number of rectangles to being 10 rectangles. And now we see that the area, I'm just going to write this down, with 10 rectangles, we see the right endpoint area is 9.48 or so. And I can also look and see when the left endpoints are given the height, we're given a value of 7.88. Let's up the number of rectangles again and say that the number of rectangles is 20. The left endpoint area approximation is 8.27, and the right approximation is 9.07. We can pause and reflect for a second. We see that the left endpoint approximations are getting bigger and bigger and bigger, which is expected because, as I notice, I can drag back and forth. With only 4 rectangles, there's a lot of white space missing. And as I get more and more rectangles, the rectangles are taking up more and more of the area under that curve. Similarly, or I guess conversely, when you're examining it from the perspective of the right rectangle, these are big overestimates. They're these big chunks that are way taller than the curve. But as I get more and more rectangles, that overestimation area gets smaller and smaller and smaller. So let's estimate a few more. Let's write down the numbers for 30. So the area for 30, again, I guess I'm at the right estimate. This is 8.93 or so, 30 rectangles. And my left estimate is 8.40. Yeah, 8.40. And my under and over estimates start converging on one another. The greatest value that I have, right when I have 50 of these rectangles, we see that my left endpoint approximation is at about 8.5, and my right endpoint approximation is at about 8.8. So they're getting closer, but I'm not quite to an exact value. This is still pretty inaccurate, and something I would need to do was to make, I could change the slider if I wanted, and I can do that by coming over to this window. I'm going to right click on the slider and go to the object properties. And let's say I want just a ton of rectangles, right? Like let's put in, I don't know if this will short out, but I'm going to try for 1,000 rectangles on this slider. Let's see what happens. So let's close this window so we can see what's going on. And if we slide this slider all the way out, you can see our area values 8.73, 8.71, 8.70. I can't even read it over here. 8.68, 8.68, 8.67. And it's going to short out with really what's going on is you could think of this as an application of squeeze theorem. My left endpoint approximations are getting bigger and bigger and bigger, so those are lower bounds on the actual value of the area. And my right endpoint approximations are getting smaller and smaller and smaller, and so that's going to be an upper bound. And these two numbers are going to squeeze together as my end values get bigger and bigger and bigger. One thing that I want to point out is that the reason why my left endpoint and my right endpoint approximations, one is lower and one is greater, is because of the shape of this curve. That you could imagine if my curve was shaping downwards or shaped differently, then a left endpoint approximation might not be an overestimate, it might actually be an underestimate, or it might be exactly right if we had, just a boring flat line. So you're going to have to look at the picture to be able to determine whether or not it's an over or an underestimate, and that's given by the fact of whether or not there's a chunk extending up beyond the curve. In this case, that's why it's an overestimate, because these rectangles are taking more space than what the curve takes up, as compared to this situation where the rectangles are taking less space than the curve takes up. Like I could look at something like 10 minus x squared as a curve, and exactly the opposite is true. So for this curve, my left endpoints give me an overestimate because there are these pieces that are above the curve.